Hey everyone, and welcome to lecture number 3. Today we're going to discuss molecular representation and geometry. So let's hop right into it. So we're going to start off by looking at this molecule here, isopropyl alcohol. So I've written some alternate names for it. You could see isopropyl alcohol, isopropanol, 2-propanol, propane 2-ol. These are all different ways to represent the same molecule with words. We can draw out the molecular formula for this, which would be C3H8O. And we know how to draw a Lewis structure for this. Isopropyl alcohol would look like this. Okay, it's a 3-carbon chain with an alcohol on the second carbon. Okay, so that would be the Lewis structure for isopropyl alcohol. We could also draw a partially condensed structure, which is what we saw in the last lecture a little bit. So we could condense some of those bonds, condense those methyl groups and just write CH3. We could also condense the alcohol and just write OH. And we'll keep this hydrogen right there. So we could condense some of the functional groups down, exclude some of those terminal H bonds to draw a partially condensed structure. And we could also draw a fully condensed structure. Now, this is useful if you're trying to type out a molecule, for example. If you're typing and you want to keep everything in one line of text, you could draw out a structure using this condensed structure, which would look like this. We'll put CH3 and then put that in parentheses and put a 2, indicating that we have 2 CH3s connected to a CH connected to a OH. So when you look at a condensed structure, it's very simple to draw, even if it looks confusing at first. All you do is read from left to right, and between each functional group or atom, you just think connected to. So I'll start on the left. We have 2 CH3s connected to a CH, connected to a OH. So we have 2 CH3s connected to a CH, which is connected to a OH. So you just read from left to right. And again, this is useful if you want to draw out a structure in one line of text. If you're writing an essay, for example, or some sort of paper, you could use the condensed structure. But the main molecular representation that we're going to discuss today for a little bit is the bond line structure. That's the one I highlighted in blue over here. This is going to be the most important one for us because we're going to start simplifying our structures and using bond line structures to represent most of our molecules from now on. Okay, so what does a bond line structure look like? Well, for isopropanol, it would look like this. Okay, for isopropanol, it would look like this. This is what you'd see if you Googled isopropanol or isopropyl alcohol, or if you Google any molecule, you would see a bond line structure. This is the industry standard for drawing molecules because, as we can see, it's much more clean and concise and easy to read. We just have to make sure we understand how to read it, okay? The first thing with bond line structures is that we draw everything with zigzags or angles like this. If we have a long carbon chain, which we'll see in the next example, we would draw with zigzags instead of straight lines like in the Lewis structure, okay? So we draw zigzags, and we also exclude all of our carbons, okay? We assume that there are carbons at the end of each line and at each vertice. So we assume that these 3 red dots are all carbons. And we also assume that all of these carbons are saturated with hydrogens. Okay, we just exclude them because they're all assumed. A lot of the compounds we'll be drawing are filled with carbons and filled with hydrogens, and it would get really messy and take a long time to draw some larger molecules if we had to draw out every carbon and every hydrogen. Okay, so bond line structure is going to be sort of our go-to method for drawing molecules. Okay, so isopropanol, again, just like this. You could technically exclude the lone pair on oxygen, but I always say for first year students, keep the lone pairs in, okay? You don't want to forget about those. Once you feel comfortable, you're more advanced, you can exclude the lone pairs if you desire, but for learning chemistry, I think it's important to keep those lone pairs in. Okay, so here we have an example that we're going to look at and break this down a little bit more slowly so we all understand it. So what we're going to do here is take this molecule, C4H10, this is butane, and we are going to represent it, we're going to draw it using bond line structure. Okay, so butane, C4H10, is 4 carbons connected in a straight chain, saturated with 10 hydrogens. Okay? Now, if we want to draw this using bond line structure, it will be much more simple and much faster. This took me a good minute to draw, and this is how quickly we can draw it with bond line structure. There we go. There's butane. So let's break that down. So we have 4 carbons, 1, 2, 3, and 4. Now, when we use bond line structure, we draw zigzags. So we'll start on the left here and just zigzag until we get 4 edges or vertices. Okay, so let's count those with red. There's our first carbon on the end. There's our second carbon at this vertice, our third carbon at this vertice, and then on the opposite end, there's our 4th carbon. So we have 1, 2, 3, 4 carbons. And for bond line structures, remember, we don't include any of the implicit hydrogens. We just assume that all of the carbons have 4 bonds and that they're all saturated with hydrogens. Okay. Okay, so there's butane, 1, 2, 3, 4 carbons in a chain. Again, we draw with zigzag line where we have 4 vertices and ends total. Okay, represented here by these red dots. 1, 2, 3, 4. What if we wanted to draw hexane, which is 6 carbons? Let's draw a 6 carbon chain. 1, 2, 3, 4, 5, 6. This would be hexane. That's 6 carbons. Let's count up. 1, 2, 3, 4, 5, 6. Okay, so there would be hexane. Let's look at maybe an example with some functionality. Let's look at this Lewis structure. What if we had CH3 and maybe we had an oxygen and then another CH3. Okay, what if we had this structure up here and we wanted to draw this with bond line? How do we do that? Well, we have 2 carbons connected together there, so we'll just draw a diagonal line. Then we have this central carbon is connected to an oxygen on top and an oxygen down here. The oxygen on top is double bonded, so let's put that in. And then this oxygen is connected to a CH3. Okay, so again, wherever we have a vertice or wherever we have a terminal line, we have a carbon. So let's put in our carbons here. I'm going to draw first up top our carbons. We have 1, 2, 3. Down here, I'm going to draw them as dots. We have 1, 2, and 3. Okay, so we have 2 carbons connected together. And then this central carbon here is connected to 2 oxygens. And then we have this terminal carbon on the end. And we can throw in some lone pairs, of course, keep those in. Each oxygen has 2 bonds and 2 lone pairs. And these carbons on the end are both CH3s. The central carbon doesn't have any hydrogens attached to it. Okay, it has 4 bonds, 2 to oxygen. I'm sorry, 3 to oxygen because it has a double bond, and then 1 to carbon. Okay, so now we're going to take it a little bit different direction. I'm going to start by drawing a structure, a bond line structure, and what we are going to do is count up the atoms in the structure. Okay, so I'm going to draw a structure here. Okay, there we go. Let me just make these a little longer so they're easier to see. Okay, so here's a bond line structure. Let's count up our carbons. I'm going to take red here. So we have carbon here at the end. We have a carbon at the vertice. We have a carbon at the vertice. Carbon here, carbon here, carbon here, and carbon here. Wherever there is a vertice or wherever there is a terminal end line, that's where we have a carbon. Okay, so let's draw out the Lewis structure off to the side here, or maybe we'll draw a partially condensed structure. We have a CH3 connected down to a carbon, which is connected to another CH3. Okay, I'm drawing the left side of the molecule here first. Now this carbon has 1 hydrogen on it because it has 3 bonds to carbons. Okay, there's the top flat bond right here is this CC double bond. So there's a double bond between those 2 carbons. That means this carbon has 1 hydrogen on it. This carbon over here also has 1 hydrogen on it because it's connected to carbon and then double bonded to carbon. And then that's connected to an oxygen and another CH3. We have a double bond, oxygens lone pairs, and there's the molecule. The trick is to make sure that carbon always has 4 bonds. If you're counting or if you're considering CH bonds, just remember the simple fact that carbon makes 4 bonds. Okay, we can't forget about that. So when we see a bond line structure like this, I'm going to draw with green this carbon right here. When we look at the bond line structure, we should be able to see that this green carbon is connected to 3 other carbons, right? The red, 1, 2, 3. So this green carbon has 1 hydrogen, 1 implicit undrawn hydrogen. This carbon right here, let's do this one in pink. This pink carbon is connected to a carbon, the green one, and it's double bonded to this red one over here. So it has 3 bonds, which means it has 1 implicit undrawn hydrogen because it has 4 bonds total. Carbon has 4 bonds, right? This hydrogen has 1 bond. I'm sorry, this carbon has 1 bond, extra bond here. And then these terminal carbons are all CH3s, right? These are all CH3s. H, 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 because these terminal carbons are only connected to 1 other carbon, so they have 3 hydrogens on them to get a total of 4 bonds. And then this final one, let's draw it in yellow. This yellow carbon does not have any CH bonds or any implicit hydrogens because it already has 4 bonds. 1, 2, 3, 4. Okay? So sometimes it can get tricky looking at bond line structures because you have to consider what hydrogens are implicit, what hydrogens are not drawn. Okay, and it's definitely a little bit of a skill, which is why we're taking some time today to practice it. I'm going to draw one more molecule here, just as practice. And as we work through the lectures in the future, we will get better and better at reading bond line structures and using them. Okay, so let me draw one more structure here just for some practice. So if we look at this structure, this bond line structure, we need to figure out what's going on. How many carbons are there? How many hydrogens are there? Just so we understand what this structure represents. Okay, let's count up everything and actually draw a molecular formula for this, and then we'll sort of make sure we understand where all these carbons are located. So I'm going to put a little dot, our little red dot on each vertice. 1, 2, 3, 4, 5, 6. So we have C6. And we know we have one oxygen. Okay, we have one oxygen, which we can see. So the question is, how many hydrogens do we have? Let's draw our implicit hydrogens, maybe with blue. So this carbon over here on the double bond, it has one carbon bond and then another double bond for a total of 3 bonds. So it has one hydrogen because it needs a total of 4. Likewise, the carbon on the other side of the double bond also has one hydrogen on it because it already has 3 bonds to carbons. So it needs one more bond for a total of 4. The carbon on the very bottom here has 2 bonds to carbons, which means it has 2 hydrogens on it. Same for the next, 2 hydrogens, and same for the next, 2 hydrogens. And the last carbon, which I will draw with green, right at the bottom of the C double bond O, already has 4 bonds, so it does not have any hydrogens. So in total, we have 2, 4, 6, 8 hydrogens. So this would be C6H8O if we were asked for the molecular formula. And maybe we'll draw out the Lewis structure over here, just so we can see exactly what's happening. We have C double bond O. This is connected to 2 other carbons. Let's start going around clockwise. We have a double bond to the next carbon and a hydrogen. We have a single bond to the next carbon and a hydrogen. And then we have a CH2. Whoops. CH2. And then we have a CH2. And then we have a CH2. Notice that all the carbons have 4 bonds. The only time carbon does not have 4 bonds is if it has a formal charge, if it has a plus or a minus. But remember, carbon should always have 4 bonds. That's the trick here, okay? Remembering that carbon makes 4 bonds and sort of figuring out how many implicit hydrogens there are, considering all the carbon bonds, okay? So hopefully you can now sort of see bond line structures. And again, consider how much faster they are to draw, right? I can draw that whole molecule in just 2 or 3 seconds rather than the 30 or 45 seconds it took for drawing the Lewis structure, okay? So that's why bond line structures are very important, very useful, and this is why we'll be carrying on for the rest of the course, mostly using bond line structure. But sometimes when there's an atom of interest, I'll draw it out specifically, such as a carbon. If we're talking about a very specific carbon, maybe I'll draw out the carbon. Other than that, though, most of them will be implicit, drawn as a bond line structure. Okay. Okay, so let's hop right into molecular geometry. I think geometry is one of the more fun and interesting topics. So the first thing that I'm just going to mention is that you'll typically see Zephyr theory or VSEPR theory when you study this or read about it. This is valence shell electron pair repulsion theory. And there are some minutiae to Zephyr theory which can be tricky to understand. but this is my entry-level chemistry definition. This is what I give first-year students who have a lot going on and just want a simple definition. Substituents on an atom tend to repel each other. That's all it means, okay? There are a lot of minutia, and you can get very detailed analysis of this, but all it means is that substituents on an atom tend to repel each other. Okay, so let's look at an example. If we took the boron atom, B, boron has 3 valence electrons, 1, 2, 3. So boron can make 3 bonds. Let's pretend we have BH3. There's BH3. So the boron atom has 3 hydrogens around it. These 3 hydrogens are going to spread out as much as possible. Okay? They're not going to sit on one side like this, right? They're going to spread out as much as possible, which is why I've drawn them the way that I've drawn them on the left here. These 3 hydrogens are going to spread out as much as possible. And it could be anything. It could be a carbon, it could be a lone pair, anything that's connected to an atom. All of these substituents will spread out as much as possible. Okay? So what is the geometry, if we were to guess the geometry of this molecule? And when I say geometry, I just mean what is the shape or the 3-dimensional configuration of this molecule if we consider that all 3 of these hydrogens will spread out as much as possible? Well, it will end up looking like a triangle, right? We have 3 substituents spread out as much as possible, and they are going to be coplanar to each other, right? They're going to be in the same plane, spread out as much as possible, where they are 120 degrees apart from each other. A full circle is 360 degrees, remember? So each of these substituents, if they spread out as much as possible, will be 360 degrees total, 120 degrees apart from each other. Okay? So looking back at VSEPR theory, we have 3 things connected to this boron atom, and we simply ask ourselves, how can these 3 things spread out as much as possible from each other? It would give you this shape, which is what we would call trigonal planar. Trigonal planar. This is our first shape, our first molecular geometry that we'll look at. Trigonal planar. Trigonal because there's 3, right? Trigonal. And planar because everything is in the same plane. Okay? This is one of the few 2-dimensional or flat molecule geometries that we'll consider. Trigonal planar. So this is when you have 3 things attached to a central atom, and those 3 things are spread out as much as possible. As we go through these molecular geometries today, at the very end, we're going to have sort of a chart to summarize everything. I'm just going to briefly explain each one first, and then we'll combine them all into a nice, handy chart that we can refer to and study from. Okay? Okay, so this is trigonal planar. 3 things spread out in the same plane. Now, for some of the other ones, we have to consider that molecules are 3-dimensional. Okay, molecules are 3-dimensional, and this can be tricky to understand for some students. It's tricky to draw 3-dimensional structures on 2-dimensional pieces of paper or a whiteboard. So what we do is we try to incorporate some 3-dimensional visuals, building a model kit. If you have a model kit, it's a great way to help understand the 3-dimensionality of molecules. And some people really struggle with that. So if you're someone who can't quite picture the molecules as we're going through them, it's a great idea to get a model kit or try to find some good visual aids online. There are some good resources online where you can get a better visual of the 3-dimensionality of these structures. Okay. So this one, there's no 3-dimensionality to it. Everything is flat. But let's take a look at another one. Let's take a look at probably the most common molecular geometry we'll see in organic chemistry. Which is the tetrahedral geometry. Tetrahedral. Okay. Real quick, a tetrahedron. Okay. A tetrahedron is the vertices of a triangular prism. Okay. Let's try that again here. Let me draw a better triangular prism. There we go. That's not too bad. So there's a triangular prism. So a tetrahedron is a shape that you get by connecting the four vertices of a triangular prism or a pyramid. Okay? So picture the molecule CH4, methane. This is a carbon atom connected to four hydrogens. And I'm going to try to draw it with some three-dimensionality, okay? The carbon here, the CH4, is in the shape of a tetrahedron where carbon is sort of in the center of this triangular prism, and each hydrogen is at one of the vertices. Okay, so these bottom three hydrogens in red, let's draw these bottom three in red, are all sort of resting on, if you have like an imaginary table here. Okay, if you have some sort of imaginary table, these three hydrogens are resting on the table in the shape of a triangle, and then that fourth hydrogen in black is pointing straight up. Now, if you tip and if you grab the CH4 and you turn it, you can place any three hydrogens down on the table, and the fourth hydrogen will stick straight up, just like a triangular prism, just like a pyramid. Okay? So it's important to understand that geometry. If that didn't quite make sense to you, I recommend building a molecular model of CH4 and holding it in your hand, turning it around, and getting a good visual of it, okay? But it's simply the shape of a pyramid. So if we consider CH4, there's a couple of things that we're going to talk about. One is going to be the coordination number. And the coordination number is simply the number of bonds, okay? So the coordination number is going to be the number of bonds. For CH4, it will be 4 bonds. Okay, CH4 has 4 bonds, so it has a coordination number of 4. How many lone pairs does CH4 have? Lone pairs, 0, right? We have 0 lone pairs. The next word is the steric number. The steric number, and the steric number is simply the combination of these two. Coordination number, or simply bonds plus lone pairs. Okay, bonds plus lone pairs. That's the steric number. So our steric number is 4. Okay. So there's a couple other words we'll look at towards the end, but for now, just make sure we understand these words that we just introduced. Coordination number, when we refer to molecular geometry, is the number of bonds that something has. That's the coordination number. Lone pairs, we know, is simply the number of lone pairs of electrons you have. And the steric number is going to be the bonds plus the lone pairs together. Okay, so this will come into play for the next structure that we look at. Again, I'm going to tabulate all these at the end. So if you're not following along 100%, that's okay. We'll have a good summary at the end where we combine everything that we learned into a nice chart. Okay, what's the next structure we're going to look at? The next shape. This is going to be trigonal pyramidal. Trigonal pyramidal. Okay, this is similar to the last shape we drew. And let's look at the structure NH3. Let's draw the Lewis structure for NH3. Nitrogen connected to 3 hydrogens, and we know we have that lone pair also. So let's note here. First, how many bonds does nitrogen have? It has 3. How many lone pairs? It has 1. So we still have 4 things connected to this atom, just like we had in the last case. The only difference here is that now we have this lone pair. Okay, so how do we go about working with that? Well, first, let's take into account the steric number, as well as the lone pairs. I'm sorry, the coordination number first. Coordination number, followed by the number of lone pairs. And then finally the sum, which is the steric number. Let's keep this box right up here. Okay, so the coordination number for NH3 is 3. That's the number of bonds. Lone pairs is 1 for a steric number of 4. Steric number you can just think of as the number of things connected to that central atom. Bonds, lone pairs, whatever it is. Okay, steric number is 4. We have 4 things connected to that central nitrogen. We have 4 things connected to it. Okay, so this, with a steric number of 4, we are again going to be sort of considering this tetrahedral shape where we have a triangular prism where nitrogen is sort of at the middle of that prism. And then we have hydrogen coming out to one side. Let's do it in a different color so it's easier to see. And then we have a hydrogen coming down here. We have a hydrogen coming down here, and we have a hydrogen going back there in the shape of a triangle, just like we had with CH4. And then the lone pair is up top here. Let's draw the lone pair in maybe blue. Now, the lone pair is deceptive, okay? It's very small. If you look here, it's just 2 little dots. But in actuality, a lone pair can exist in a large quantity of space. So don't think lone pairs are small because they're just 2 little dots, because we can draw them bigger, right? You just typically see them as 2 little tiny dots, but lone pairs are actually quite large, okay? Lone pairs can be quite large. So the lone pair takes up a lot of space, but we still have 4 things connected to this central atom, in this case, nitrogen. So all of these 4 things are still in the shape of a pyramid. However, when we consider molecular geometry, we don't consider the lone pairs. So when we consider the geometry of a molecule, all we consider is the bonds. We consider how the bonds are shaped. Now, the lone pairs can influence the shape of the molecule by existing, but when we consider the actual shape, we pretend like they're invisible, okay? So if we pretended like the lone pair was invisible, nitrogen would look something like this. NH3, we'd have sort of a pyramid where these 3 hydrogens are coming down and away from the nitrogen in the shape of a triangular prism. And then again, up above the nitrogen in this space up here is the lone pair, which is pushing these nitrogens down. Remember, everything wants to spread out as much as possible. And a tetrahedron or a triangular prism is the best way for 4 things to spread out from each other as much as possible. Okay. So this would be considered trigonal pyramidal. Trigonal pyramidal. This is our next molecular geometry. Trigonal because it has 3 bonds, and pyramidal because it's in the shape of a pyramid. Okay, easy enough to remember. Now let's talk quickly about some bond angles here, which are interesting. So in our last example, let me draw CH4 right up here. In our last example, we saw CH4. This is a perfect tetrahedron. It's equal in every direction, CH bond in every direction. The angle between these bonds, the angle is going to be 109.5 degrees. Okay, that's the angle between each bond in a perfect tetrahedron. Now looking back at our trigonal pyramidal structure here, where we have this big lone pair up above nitrogen, this is the key aspect to think about for when we think about VSEPR theory, is that lone pairs have a bigger repulsion than single bonds. Let me draw that down here in text, just so we get that. Lone pairs repel more strongly than single bonds. Okay, this is important. Lone pairs repel more strongly than single bonds. So if we have a stronger repulsive force from these electrons up here, you can imagine how these hydrogens here are going to be pinched a little bit closer together. They're pinched a little bit closer together than they would be in the typical tetrahedron. Okay? And that actually is measurable. And we have determined that the angle between hydrogens here, the angle between hydrogens is no longer 109.5, but it's down to 107. So again, the lone pair has more repulsive force than single bonds. So when all these 4 things are spread out as much as possible, but that lone pair sort of pushes everything a little bit further away from it, pushes those hydrogens just a little bit further away, which pulls them closer together on the opposite side of the nitrogen. Okay. So the bond angle gets a little bit smaller here, down to 107. Okay. So there's trigonal pyramidal. We have 3 bonds with 1 lone pair. That gives us a steric number of 4. This is going to give us a trigonal pyramidal structure or geometry. Okay. So let's look back at trigonal planar. One more time, just to make sure we know what we're talking about. So we had the example with boron. Boron is very common, also aluminum. Let's do BF3 this time. This is a reagent we might see in the future. BF3, very similar to BH3, except now we have fluorines instead of hydrogens. You could include all the lone pairs here if you want to be concise. I recommend first-year students to always draw those in. So let's look at trigonal planar. We have BF3, our coordination number is 3, our lone pairs are 0, so our steric number is 3. So we have 3 things, 3 single bonds, spread out from each other as much as possible. They'll be in the same plane from each other with an angle of 120 degrees apart, because that's the furthest that you can spread apart 3 things, right? If we have a circle, if we have a sphere, we put 3 things on it, those 3 things will spread out as much as possible, which means they will become coplanar and spread out at 120 degrees apart. Okay, so that one's pretty straightforward, pretty simple. Let's continue on to our next geometry. Okay, the next shape we are going to consider is bent. And the most common example that you see is H2O, water. Water is a bent molecule, bent geometry. So let's draw this out. Let's draw the Lewis structure for water. We have oxygen. We have 2 lone pairs and 2 bonds. We have hydrogen and we have hydrogen. So you can probably see just from the Lewis structure why we consider it bent. But let's break this down into more detail. Again, just like in the previous examples, we have a steric number of 4. In this case, we have 2 lone pairs and 2 bonds, but we have a steric number of 4. And once again, that oxygen you can picture in the middle of a pyramid where at each vertice we have one of these 4 things, okay? You can see why the tetrahedron is so important in chemistry. We have a hydrogen at one, we have a hydrogen at the other, we have a lone pair down here, and we have a lone pair up here, okay? All 4 vertices of that pyramid where oxygen is in the center of the pyramid. Whenever you have a steric number of 4, those 4 things will spread out in the shape of a tetrahedron, okay? Very important concept. So if these 4 things are spread out in the shape of a tetrahedron, but when we consider molecular geometry, we ignore the lone pairs, we can see how the shape of this molecule is simply a bent structure. We go from hydrogen up to oxygen, and then from oxygen back down to hydrogen. Okay, again, we ignore those lone pairs when we consider the geometry. Now, if we consider our previous examples, where we had CH4 and NH3, and we considered the angles here, where this is 109.5 in a perfect tetrahedron. In the case of the NH3, we get extra repulsion from the lone pairs, so this angle becomes 107. Now, if we have 2 lone pairs, hopefully you should understand that we should have these hydrogens pushed even closer together at 105. Why? Because remember, lone pairs have more repulsion, have a stronger repulsive force than single bonds. They take up more space. They have a harder push. So those 2 lone pairs on top are pushing those hydrogens even closer together on the far side of the molecule, giving them an angle of 105. Okay, so we have a coordination number of 2, we have 2 lone pairs, we have a steric number of 4, and we have a molecular geometry which is bent. Okay. Okay, our final molecular structure is linear. Linear. Now, there's not a lot of linear compounds that we'll see. There are a few. Carbon dioxide, for example, is linear. Carbon double bonded to 2 oxygens. I think we saw that in a previous lecture. The one we'll look at here today is beryllium hydride, BeH2. Okay. Beryllium, like oxygen, forms 2 bonds. If we look at the periodic table, we will see that beryllium has 2 valence electrons. If we make 2 bonds to beryllium, we could envision how those 2 bonds would spread out as much as possible, which means they would be on opposite sides of beryllium, right? Vesper theory, things are going to spread out as much as possible. So these 2 hydrogens will spread out as much as possible, giving us a straight line. Quite obviously, this would be 180 degrees. They are on opposite sides of beryllium. Considering our coordination number, we have 2 bonds. We have 0 lone pairs, which gives us a steric number of 2. Okay, so that's all of our molecular geometry. Now I'm going to summarize it all in a chart. And this chart is going to be something that you should look at and study and make sure you understand. Then we'll do a couple practice problems. Okay, so let me draw out this chart here. Okay, so here's our chart summarizing all of our molecular geometry using all the examples that we just saw. Now I added one extra column here towards the right called electron geometry. This is something you may see on your exam. It's not It's not seen all the time, but we should be aware of what electron geometry means. I'll explain that once we get there. So let's start at the top here with CH4 with methane. The coordination number, or the number of bonds, that would be 4. The number of lone pairs, 0. The sum of these two numbers is the steric number, which is 4. And we said our molecular geometry is tetrahedral. Tetrahedral. The vertices of a triangular prism. Okay, a very important shape. Now, the electron geometry is going to change. It's not always going to be the same as molecular geometry, but for the electron geometry, you also consider lone pairs. Let me write that here. So electron geometry includes the lone pairs in the geometry. Molecular geometry ignores them, okay? Molecular geometry ignores the lone pairs. Electron geometry includes the lone pairs. Molecular geometry, the one on the far right, this is the more common column that you'll see, and when you consider molecular geometry, that's the one that most people are talking about, okay? So for CH4, if we include our lone pairs, we don't have any, so the electron geometry stays the same. So it's tetrahedral also. Let's look at NH3, ammonia. We have 3 bonds, and we have 1 lone pair, which gives us a steric number of 4. 3 bonds, 1 lone pair, sum them together to get 4. We said that the molecular geometry is trigonal pyramidal. Trigonal pyramidal, shaped like a triangular pyramid, shaped like a prism. And the electron geometry, if we include the electrons, it's still shaped like a tetrahedron. So this has tetrahedral electron geometry. Because remember, for nitrogen, let's draw it over here. We have NH3, and then we have that lone pair up top here. I'm going to draw like a bond to the lone pair. We can picture that lone pair sort of being connected to that nitrogen. We can see how if we include the nitrogen, if we include the lone pair, it's shaped like a tetrahedron. It's shaped like the CH4, right? So if we include that lone pair, we have tetrahedral electron geometry. If we ignore it, if we ignore that lone pair, we have the triangular prism down here, the trigonal pyramidal structure. Okay. Next, we have H2O. H2O has 2 bonds, 2 lone pairs, steric number of 4. Okay, once again. So if we have a steric number of 4, once again, we have 4 things connected to this oxygen. We have 2 hydrogens and 2 lone pairs. So those will spread out from each other in the shape of a tetrahedron. But if we consider just the molecular geometry, just the bonds, this would be bent. That is a bent geometry. The next one we looked at was BF3. We have 3 bonds. We have 0 lone pairs, giving us a steric number of 3. So this is the first one we see with a different steric number than 4. So if we consider the electron geometry, this would be trigonal planar, which is the same as the molecular geometry. Trigonal planar. Okay. Remember BF3, those 3 things attached to boron, whether they be fluorine, hydrogen, whatever's attached to that boron, is going to be spread out as much as possible from each other, according to VSEPR theory. So they will become coplanar, or on the same plane, and spread out 120 degrees from each other. This is a trigonal planar structure. We have no lone pairs, which means the electron geometry is the same as the molecular geometry. And then finally, we have beryllium hydride, BeH2. We have a coordination number of 2 with 0 lone pairs, giving us a steric number of 2. If we have 0 lone pairs, again, that means the electron geometry will be the same as the molecular geometry. Both of these are linear. Okay, so we could note here that the only time we have lone pairs is with these two here. So that will give us either a trigonal pyramidal or a bent molecular geometry. Other than that, if we don't have any lone pairs, it'll be tetrahedral, trig planar, or linear. Okay. And you should really be aware of that tetrahedron. Very important to understand that shape. Okay. Whenever we have a steric number of 4, whenever we have 4 things connected to an atom, those 4 things will spread out in the shape of a tetrahedron because that's the furthest they can get apart from each other. Okay. Okay, so make sure you understand this chart. Review it again if you need to. I'm going to run through a few practice problems here where we consider the molecular geometry of a few structures, and then we will see more practice problems in the upcoming workshop dealing with molecular geometry. Okay. So first, let's consider, let me do it in black here. Let's consider the molecular geometry of H3O+. This is known as a hydronium ion. Hydronium ion. Okay. This is water with an extra hydrogen. We call it a protonated water. We'll learn more about that in the acid-base chapter. But for now, let's consider the molecular geometry of it. So how can we consider that? Let's start by drawing the Lewis structure nice and clearly. We have oxygen, and we have 3 hydrogens on it. 1, 2, 3. Now, if oxygen is positively charged, that means we have 3 bonds and we have 1 lone pair. 3 bonds and 1 lone pair. Okay. Hopefully you remember that from the formal charge section after looking at that workshop and lecture. Oxygen with 3 bonds and 1 lone pair is positive. Okay. If you didn't remember that, you would have to go back to the periodic table, look up oxygen, see that it has 6 electrons, and then compare it to how many electrons it does have. If it's positive, that means it only has 5 electrons. Okay, which means it's making 3 bonds with 1 lone pair. Okay. So here's our structure. We have a steric number of 4. Let's draw that over here. Let's draw our coordination number, lone pairs, steric number, and then we'll do our electron geometry and our molecular geometry. Okay, let's break it down all the way. Coordination number of bonds is 3. Lone pairs is 1. That gives us a steric number of 4. And anytime we have a steric number of 4, we have 4 things connected to an atom. That gives us a tetrahedral geometry for the electrons. But if we ignore the electrons, remember that's the molecular geometry. If we ignore the electrons, what shape do we have? I'm going to draw it differently over here. We have oxygen with 3 hydrogens. I'm going to draw them in the shape of a tetrahedron and then a lone pair. Again, spreading out to the vertices of a triangular prism. Okay, a little bit difficult. I'm not the best artist, but hopefully you can see that oxygen has 3 hydrogens, each spreading out to the vertices of a triangular prism, and then the lone pair on top. So if we ignore the lone pair, what's our geometry? It's trigonal pyramidal. We have a pyramid. Okay, trigonal pyramidal. Just abbreviate it there. Trigonal pyramidal. I'm just going to put trig pyr. This is similar to our NH3. If you didn't quite follow that, but you understood the previous example, this is similar to our NH3. We have a nitrogen with 3 hydrogens and a lone pair. And we have an oxygen with 3 hydrogens and a lone pair. Same sterics, but in this case, it's an oxygen with a positive charge, but it doesn't matter, right? This lone pair and these atoms out here, they don't think about what they're connected to when they spread out. They just want to spread out as much as possible. Okay, so they're going to spread out in the shape of a trigonal pyramidal structure if we ignore the lone pair. If we also consider the lone pair, the electron geometry, it would be tetrahedral. But again, the electron geometry here, not all the time it's seen, depending on your professor, depending on the requirements for your organic sequence. A lot of times you'll just see molecular geometry. You'll just see this one, which in this case, we ignore the lone pair, but it still has an influence, right? It still has an influence on those hydrogens. It pushes them down, but we simply don't consider it. We pretend it's invisible when we look at the structure. So we would consider this trigonal pyramidal. Okay, what about NH4 plus? Now we saw this structure before. This is the ammonium ion, NH4 plus. So we have nitrogen connected to 4 hydrogens. This is similar to our CH4. We have carbon with 4 hydrogens. We have nitrogen with 4 hydrogens. Same geometry, same everything. We have a coordination number of 4. We have 4 bonds. We have 0 lone pairs, which gives us a steric number of 4, and a molecular geometry that is tetrahedral. Our electron geometry would also be tetrahedral if we were asked that, because there's no lone pairs. So it doesn't matter if the lone pairs are there or not. This has a geometry of tetrahedral. Okay, easy enough, just like the CH4. And finally, let's look at a carbocation. We're going to see these much more often in the future, but for now, let's consider this carbocation. Now, a carbocation has 3 bonds and 0 lone pairs. Remember up top here, carbon should have 4 electrons. If carbon has 3 electrons, that means it's positive. We're missing an electron. So a carbocation is a carbon that only has 3 bonds. It becomes positively charged. We call it a carbocation. So let's take a look here. This one we'll draw out. We have a coordination number of how much? 3. 3 bonds. Lone pairs, we have 0. And our steric number is 3 plus 0, which is 3. And then we will consider the molecular geometry and the electron geometry. Okay, so if we have a central atom and we have three things connected to it, what's that similar to? That's similar to our BF3 example, where these three things will spread out as much as possible. And the best way for them to do that is to become coplanar, to become flat, all on the same surface. Imagine you're putting it on a table. All three of these are together, laying together on the table, and then spread out 120 degrees apart from each other. Okay, they're all spread out in a perfect circle, 1, 2, 3, as far away as possible, which gives us a trig planar. Make sure you don't confuse trigonal pyramidal and trigonal planar. Trigonal planar means they're all in the same plane. We can get trigonal pyramidal if we added a lone pair to here, right? So right now, all three of these, if we look at BF3, F, F, and then in the back, F, all on the same plane, like a carousel. If we were to somehow add a lone pair up here, now boron can't take a lone pair, but if it was possible to add a lone pair up here, this would instantly push those fluorines down, push them down into the shape of trigonal pyramidal, right? It would push those down into the shape of trigonal pyramidal. But again, boron doesn't have a lone pair. It's just a theoretical situation, right? Boron gives us this planar structure. Trig pyramidal, this would be something like nitrogen. If we had nitrogen with a lone pair, say we had NF3, that would be trigonal pyramidal, okay, shaped like a pyramid. So make sure you don't confuse those. And again, the electron geometry, if we include the lone pairs in our geometry, it will still be trig planar because we don't have any electrons, okay? All right, so there's a few practice problems. We will see many more in the workshop, in the next workshop. Overall, geometry is not too difficult. The key concept is really just understanding the shapes and being able to picture them. If you can't picture them, build a model, get a model kit, or perhaps find a good video online where you can see the molecules in 3 dimensions if you're having a hard time visualizing it from my description and my substandard artwork. Okay. All right, thanks for joining me for this lecture, and I will see you guys in the next video, lecture 4.